Okay, so moving on to the 3D gas laws. We're going to start with the combined gas law first. And as the name implies, this is actually the combination of a number of the four laws that we just talked about, a number of the 2D laws. So here we have Boyle's law, pressure over inverse volume. We have Charles' law, volume versus temperature. And we have Gay-Lussac's law, pressure versus temperature. Now, each one of these parameters represents a specific way of looking at a gas. But in essence, a gas will basically exist with a pressure, a volume, and a temperature at any given point in time. So you could actually combine all three of these parameters and look at it in a 3D way. Now, the way I'm depicting this, you only have two axes. But if you actually were to incorporate pressure, volume, and temperature, you will actually look at something like this. Okay, you have volume on this axis, you have pressure on that axis, and you have temperature on this axis. And as you can see, the graph is rather complicated. And this is some of the topics that you would talk about in physical chemistry, which is an upper division chemistry course, or even in material science and potentially thermodynamics. Like for those of you who are studying engineering, you will probably see and study this once you get to your upper division engineering courses. And if you're a material scientist, most likely not, you will have to look into this. But needless to say, the actual information is drastic and is complex. And there's regions right here which actually stand for metastable states that you can actually have gases for some short period of time. Now, needless to say, this is way too complicated for the intent and the actual thing that we're trying to teach you in chemistry, general chemistry 1. So instead of dealing with that, what we're going to do is just do what the name of the law says. We're going to combine these three things into an equation. And the idea is this. If you look at it from the point of view of the slope, pressure times volume equals the slope of the line. Volume over temperature equals the slope of the line. And pressure over temperature equals the slope of the line. So notice that the volume and pressure are always on top of the equation and the temperature are always on the denominator of the equation. So if you literally jam them together, you're going to end up with P times V on top of the equation and temperature on the bottom of the equation equaling some constant. This right here becomes the premise for the combined gas law. Specifically, P1 times V1 over T1 must equal P2 V2 over T2. So here we're definitely jamming everything together. And this is the way in which we're going to think of the combination of these three gas laws. We're not going to deal with the crazy graph I just showed you. That was just for reference. But this is the thing you need to be aware of. Now, this has to be done a constant number of moles, by the way. But here's a problem that depicts all of this. In essence, we have a gas, it always has to be a gas, that has a given pressure, 705 millimeters mercury. The pressure is changing to 760 millimeters mercury. So now we have a set of pressures right here. Okay, so that looks like it's going to be part of the game. We have a volume of 3 liters. And we're trying to find out what the volume is going to be at the end. So now we have two sets of volumes. And we have an initial temperature right here and a final temperature. So we have pressure, temperature, and volume all changing. We have sets of 2's for all three of those parameters. So this is telling you this is the combined gas law. And one more thing before I get into the actual input of numbers. Notice that I have here STP conditions written. I'm going to be a little bit more obvious as to what that means when we talk about the ideal gas law, but for reference, STP stands for standard temperature and pressure. And for gases, the standard temperature is 273 Kelvin and the standard pressure is 1 atmosphere or 760 millimeters mercury. So that's something I need you to remember. Standard temperature 273 Kelvin, pressure 1 atmosphere for gases. All right, now we're looking for the final volume. So that means that we need to isolate for V2. That implies that we need to multiply both sides by T2 and we need to divide both sides by P2. So this will be the setup for which you will end up solving the the value for the second volume. Now, you have a lot of variables present in here, and it will be rather easy, even for me, to mess up the order of these things. So what I kind of recommend that you do is on the side, write P1 equals 705 millimeters mercury, V1 equals 3 liters, P2 equals 760 millimeters mercury, T2 is 273 Kelvin, and so on and so forth. Like actually write it out here on the side before you start plugging it in, so you don't make the mistake of putting things in the wrong place. However, if you feel pretty confident of being able to read the paragraph or the couple of sentences and know which one is P1, V2, etc., then you can just go directly. Alright, so P1 is 705 millimeters mercury. You have your 3 liters for V1. T2 is your 273 Kelvin, so that's what needs to go on top. On the bottom, you need T1, which is your 308. Alright, so 308 Kelvin. And your P2, which needs to go on the bottom, is your 760 millimeters of mercury. Okay, so everything cancels out here in terms of units. The millimeters mercury go away, the Kelvin go away, and all that you're left with is liters, units of volume. So you want to multiply 705 by 3 liters by 273, press enter, divide by 308, press enter, divide by 760, press enter, and you should find out that the volume ends up being 2.47 liters altogether. Now the only problem with the combined gas law is that you don't really have a good sense of whether your answer is correct or not, because you have multiple things happening. Things that decrease or are inversely related to each other, and then you have things that are directly related to each other, and they kind of like do opposite things. So it's not simple to look at the numbers and say, oh, you increase the pressure, so the volumes have to increase. You can't do that. So you have to be very careful with how you input and what you input into your variables here when using the combined gas law, because at the end you'll get a number. You will always get a number, but if you have input the wrong things in the wrong places, this answer will be wrong, and you won't have a good way of gauging whether your answer is right or not, at least not for the combined gas law. Alright, now what I'm going to talk to you about next is the ideal gas law. So we'll stop this video right here, and in the next video we'll talk about the ideal gas law.